The topic of today lecture is differential operators. It is chapter 4 linear differential equation of higher order and section 4.5 differential operators. You know that dy by dx is the derivative of y with respect to x, and we also denote the differential operator as d of y. The symbol d is called the differential operator. Why we call it differential operator? Because it transforms a differentiable function into another function. It transforms a function into another function. Uh, because of this, we call it a differential operator. Let d is applied. Differential operator is applied on cos 4x. So we take the derivative of cos 4x, which is minus sin 4x into 4. And if we apply differential operator on a polynomial, then we apply it term by term. First we apply it on 5x cube. We get 5 is a coefficient, and for x cube we get 3x square, so it becomes 15x square. Then it minus sign remains same, and then the differential operator will apply on this, and it will 6 will is coefficient, it remains same, and the derivative of x square is 2x, so it becomes minus 12x. So first one derivative is dy by dx, and if we take a second derivative, then we write derivative of dy by dx with respect to dx, or d square y over dx square. So we can also write it as d into dy or d square y. So if we write nth derivative, then we will write it d raised to power n y. We can also find a differential. We can also write differential operators as a polynomial d plus 3 d square plus 3d minus 4, and with variable coefficients also. So the nth order differential operator or polynomial operator can be written as anx d raised to power n. Anx is coefficient of d raised to power n. An minus x is the coefficient of the differential operator n minus 1, and so on. So differential operator is actually a linear operator. We can extract the coefficient out, and we can also apply it term by term. So differential operator is a linear operator. We can if we write the linear combination of the differential operator as L, then the linear combination of the differential operators when applied on two functions alpha x and beta x, two functions fx and gx, where alpha and beta are constant, can be written as alpha, the coefficient comes out alpha L of f of x plus beta L of g of x. So we can say that the linear combination of operators is also linear, where L is a linear operator. Now if uh, we have a differential equation, this we can write it in the form of differential operator as for y double prime we can write d square y, for y prime we can write dy, and y is equal to f of x minus 3. So this differential equation can be written in the form of differential operator, and all these terms have y, so we take y common, and there is it become a polynomial, second degree polynomial of differential operator. So if we write it as L, so it become Ly is equal to g of x. Similarly, for homogeneous equation, it will become Ly is equal to 0. We can also factor the linear combination of differential operators. as we factor a polynomial. So let's suppose we have d square plus 5d plus 6, or we have a differential equation which in the form of differential operator can be written as d square plus 5d plus 6y. So first of all we will factor these. So you can see that if we take 2 and 3, then 2 into 3 is equal to 6 and 2 plus 3 is equal to 5. So we can factor them as d square plus 3d plus 2d plus 6, and taking d common we get d plus 2 and d plus 3. So a differential operator can be factorized. We can write it d plus 3 into d plus 2, or d plus 2 or plus into d plus 3. So if it has constant coefficient, then the factors of a linear differential operator can commute, follow the commutative property. Here is a question of exercise 4.5, question number 5. Write the differential equation in the form of Ly is equal to g of x, where L is a linear differential operator with constant coefficient. So for y triple prime we write d cube y minus 4, for y double prime d square y, and plus 5 for y prime we write 5d y, and taking y common we get this linear operator L is equal to 4x. So we write it in the form Ly is equal to gx. Question number 13. If possible, factor the differential operator d cube plus 2d square minus 13d plus 10. Since it is a polynomial of degree 3, so we need to find one factor of this polynomial. Uh, it has a constant. The fourth term is a constant 10. So we can take the its factor, the factors of 10. So the factor of 10 are 1, 2, 5 and 10. So taking 1 or take 2, and the factor we can take plus minus also, plus minus 1 plus minus 2 plus minus 5 plus minus 10. So here I take d minus 2 as a factor. So if d minus 2 is equal to factor, then d is equal to 2. We put d is equal to 2 in this polynomial, and when we put d is equal to 2, we see that d cube 2 cube 8, 2 cube 8 plus 2 into 2 square 4, 4 2s are 8, minus 13 2s are 13 2s are 26 plus 10. It gives 8 plus 8 16 plus 10 26 minus 26. So it gives 0. So one of the factor is d minus 2. Now to get other factors, we will divide this polynomial by d minus 2, the first factor. So it is a long division. We to get d cube, we multiply d by d square, and then we get d cube, and then we multiply minus 2 with d square, we get minus 2d square. Then we subtract these two. Here we get minus d3, and here we get minus d3, and here we get plus 2d square. Now it will become 4d square. D cube minus d cube is cancel out, and 2d square becomes 4d square, and we pull down these two also. Then we to get 4d square we multiply d by 4d. So we get 4d square, then we multiply minus 2 by 4d, we get minus 8d. Then by changing sign we get minus 4d square and plus 8d. So it's the d square terms cancel out, and from here we get minus 5d plus 10. 10 comes down. Then we multiply d by minus 5. To get minus 5d, and we multiply minus 2 by minus 5, we get plus 10. So by changing the sign, we get here minus 5d and here minus 10. So minus 5d plus 5d we get 0, and 10 minus 10 we get 0. Now it is completely divide and remainder is 0. So the divisors of these, the vectors of this polynomial is d minus 2 and d square plus 4d minus 5. We further divide this quadratic polynomial, we can see that we can have two factors 5d and minus d, so that 5 into minus 1 is minus 5, and 5 into 5 minus 1 is equal to 4d. So we factorize it, and taking d common here, and from here we take minus 1 common, so we get d minus 1, and when we take d from here we get d plus 5, also d plus 5 from here, so the third factor is d plus 5. So this way we can factorize the differential operator. The second operator is called annihilator operator. If L is a linear differential operator with constant coefficient and f is sufficiently differentiable function such that if we apply the differential operator on f we get 0, then L is said to be an annihilator of that function. It annihilates that function. So if we take any constant function y is equal to k, and we apply d on it, then the derivative of constant is 0. So d annihilates this function, or y is equal to x is annihilated by the differential operator d square. When we apply, when we take 2 times derivative of x, we get 0. Similarly, by taking 3 times derivative of x square, we get 0. So we can, in general, we can write the differential operator d raised to power n annihilates the function x raised to power n minus 1, and also other which have less power than xn minus 1. If we take d minus alpha raised to power n, then it annihilates the function e raised to power alpha x, x e raised to power alpha x, so on till x raised to power n minus 1 e raised to power alpha x. How can we say that? Because if we write it in terms of differential equation, a homogeneous differential equation, then we can write d minus alpha raised to power n y is equal to 0, and its auxiliary equation will be m minus alpha raised to power n is equal to 0. We will get uh, alpha as a root of multiplicity n, so its general solution will be c1 e raised to power alpha x plus c2 x e raised to power alpha x, and so on, plus cn x raised to power n minus 1 e raised to power alpha x. So this means this function annihilates these all, so that we get 0. The differential operator d square minus 2 alpha d plus alpha square plus beta square whole raised to power n annihilates each of the function. How can we say that? If we write this operator in the form of homogeneous differential equation, this operator y is equal to 0, and by solving we get the complex roots. So the complex roots of multiplicity n. So we can write the complex root alpha plus minus beta iota raised to power n. So the complex root is alpha plus minus iota beta raised to power n. So the general solution of this will be e raised to power alpha x cos beta x plus sin beta x plus x e raised to power alpha x cos beta x plus sin beta x, so on till x raised to power n minus 1 raised to power alpha x into cos beta x plus sin beta x. Now the question of exercise 4.1, question number 29. Find a linear differential operator that annihilates the function e to the power minus x plus 2x e to the power x minus x squared e to the power x. Now we need to find the linear differential operator and function is given. We know that d minus alpha annihilates the function e raised to power alpha x. So here are two functions, e raised to power minus x and e raised to power x. And e raised to power x comes with x and x square. So this means we have actually two operators. One is for e raised to power minus x, here alpha is minus 1. So we can write its linear differential operator as d minus minus 1, means d minus minus 1. So it's d plus 1. And for e raised to power x, we can write d, here alpha is 1, so we can write d minus 1. But here we get x e raised to power x and x squared e raised to power x. This means that d minus 1 has multiplicity 3. It has power 3. So d plus 1 into d minus 1 cube annihilates this function. You can also check whether it annihilates or not by simplify the cube and taking the product and then apply on this function, and you will get 0. Question number 35. Find linearly independent functions that are annihilated by the differential operator. Here we need to find functions and differential operators are given. D minus 6 to d plus 3. We will use this because it is the linear form d minus alpha. The first one is d minus 6, which looks the same like d minus alpha. So here alpha is 6. So the function is e raised to power 6x, which is annihilated by d minus 6. So we write here e raised to power 6x. So to find the second function, which is annihilated by 2d plus 3, because here the coefficient of d is not 1, so we first convert it into 1. So first we write this as a homogeneous differential equation. 2d plus 3y is equal to 0. We need to find y. So what we do to make the coefficient 1, the coefficient of 2d 1, we will divide it by 2. So we divide and multiply by 2, and this 2 goes to right. Here it's multiplying, so to right it will be divided. 0 divided by 2 is equal to 0. Now we separate it term by term. 2d by 2 is d plus 3 by 2. Y is equal to 0. This means d plus 3 by 2 annihilates y. So what is y here? By looking at this, we can say that alpha will be minus 3 by 2. We can write d plus 3 by 2 as, we can write d plus 3 by 2 as d minus 3 by 2. So here alpha is minus 3 by 2. So the function which is annihilated by this operator is e raised to power minus 3 by 2 x. Thank you very much. Do exercise 4.5. If you find any problem in it, you can ask me in comments. I hope you understand this lecture. Thank you very much.